The James Webb Space Telescope just recorded something with the interstellar object 3I Atlas that scientists are calling completely unprecedented. What Webb saw shouldn't be possible according to everything we know about space objects. This isn't just another asteroid passing through our solar system. This is an object that came from another star system entirely. And what it's hiding could force us to rewrite our understanding of how objects form in the depths of space. 3I Atlas appeared in our sky seemingly out of nowhere, traveling at incredible speeds from a direction that proved it didn't originate in our solar system. When astronomers first spotted it, they knew immediately this was something special. The object was moving too fast to be bound by our sun's gravity. Its trajectory showed it was just passing through, a visitor from the vast space between the stars. But that was only the beginning of the mystery. When ground-based telescopes first detected 3I Atlas, scientists scrambled to gather as much data as possible before it disappeared forever into the darkness of space. These kinds of opportunities don't come often. Before 3I Atlas, we had only detected one other confirmed interstellar object passing through our solar system. That object, called ʻOumuamua, caused its own share of controversy and confusion when it arrived in 2017. ʻOumuamua had a strange, elongated shape and moved in ways that seemed to defy normal physics. Some scientists even wondered if it could be artificial, though most dismissed that idea. Still, ʻOumuamua showed us that interstellar objects exist, and they can be very different from anything in our own solar system. So when 3I Atlas appeared, astronomers were ready. They had learned from the ʻOumuamua experience. They knew they needed to observe quickly and thoroughly before the object flew past and was gone forever. Ground telescopes around the world turned their attention to this cosmic visitor. They measured its speed, tracked its path, and tried to figure out what it was made of. The initial observations were puzzling. 3I Atlas didn't behave quite like astronomers expected. It had characteristics that seemed strange for a typical comet or asteroid. The object showed signs of activity, releasing gas and dust like a comet would when heated by the sun. When comets get close to our sun, the ice on their surface turns directly into gas without melting into liquid first. This process is called sublimation. The gas and dust released from the comet's surface creates the beautiful tail that we see in the sky. Comets from our own solar system do this all the time. It's completely normal behavior for an icy object approaching the sun, but 3I Atlas was doing something different. The amount of gas it was releasing didn't match what scientists expected based on how far it was from the sun. Comets brighten in predictable ways as they approach the sun. The closer they get, the more ice sublimates, the more gas they release, and the brighter they become. Scientists have formulas to predict this brightness change. When they applied these formulas to 3I Atlas, the numbers didn't add up. The object was releasing more gas than it should have been at its distance from the sun. Either 3I Atlas was made of ice that was much more easily vaporized than normal comet ice, or something else was going on that astronomers didn't understand. Some scientists suggested that 3I Atlas might not be a solid object at all. Perhaps it was actually a loose collection of smaller pieces held together weakly by gravity, like a flying rubble pile. If that were true, the object could be breaking apart as it traveled through space. When pieces broke off, they would expose fresh ice underneath that would immediately start releasing gas. This could explain why 3I Atlas was so active. The breakup hypothesis made sense in some ways, but it created new questions. Why would an interstellar object be so fragile? Objects that survive the journey between star systems should be tough, not delicate. This is where the James Webb Space Telescope entered the story. Webb is humanity's most powerful space telescope, designed specifically to see things that no other telescope can see. Unlike Hubble, which observes mainly invisible light like our eyes do, Webb observes in infrared light. Infrared light is essentially heat radiation. Everything that has temperature emits infrared light. The hotter something is, the more infrared light it emits, and the shorter the wavelengths of that light. Webb's infrared vision allows it to see warm objects in space, including the gas and dust around comets and asteroids. Webb's giant mirror collects faint infrared light from across the universe. The mirror is over 6 meters wide, much larger than Hubble's mirror. This size matters because bigger mirrors can collect more light, allowing Webb to see fainter and more distant objects. The mirror isn't a single piece of glass. It's made of 18 separate hexagonal segments that work together as one mirror. Each segment is coated with a thin layer of gold because gold reflects infrared light extremely well. The segments can be adjusted individually with incredible precision to keep the whole mirror perfectly aligned. The telescope operates in a special location in space called the second Lagrange point. This spot is about 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravity from the Earth and Sun balance perfectly, allowing Webb to stay in one place relative to Earth, without using much fuel. More importantly, this location keeps the telescope in Earth's shadow, away from the bright light and heat of the Sun. Webb needs to stay extremely cold to detect faint infrared signals from space. If the telescope itself were warm, its own heat would overwhelm the faint signals it's trying to detect. A massive sun shield the size of a tennis court protects Webb from the sun's heat. This shield has 5 layers of special material that reflect and absorb the sun's energy. The sun-facing side of the shield gets scorching hot, reaching temperatures that could boil water. But the telescope side of the shield stays incredibly cold, colder than -200 degrees Celsius. This extreme temperature difference is crucial for Webb's sensitive infrared detectors to work properly. Cold detectors can pick up faint heat signals from objects billions of kilometers away. When scientists pointed Webb at 3I Atlas, they expected to learn more about the object's composition and activity. What they didn't expect was to find something that would challenge our basic understanding of interstellar objects. Webb's infrared sensors picked up details that ground telescopes had completely missed. The patterns of gas and dust around 3I Atlas told a story that didn't make sense according to conventional wisdom. Webb detected specific chemicals in the gas coming off 3I Atlas. By analyzing the wavelengths of infrared light the gas absorbed and emitted, scientists could identify what molecules were present. They found water vapor, which was expected since comets are largely made of ice. They found carbon dioxide and carbon monoxide, also common in comets. But they also found more complex organic molecules, carbon-based compounds that are the building blocks of life. The presence of these molecules wasn't shocking by itself. Scientists know that space contains many organic compounds. Meteorites that fall to Earth often contain amino acids and other organic materials. What was shocking was the amount and variety of these compounds coming from 3I Atlas. The organic molecules were far more abundant than they should have been for an object of this size and temperature. In our solar system, comets contain some organic material, but mostly they're made of simple ices like water, carbon dioxide, and methane. The organic content is a small fraction of the total mass. But 3I Atlas seemed to be releasing organic molecules at a rate that suggested they made up a much larger portion of its composition. It was as if this interstellar visitor was made of fundamentally different stuff than the comets born in our own solar system. Webb also detected unusual patterns in how the gas was being released. Normal comets have 1 or sometimes 2 jets of gas streaming away from specific spots on their surface. These jets form because the comet is rotating and different parts of its surface face the sun at different times. When a particular spot rotates into sunlight, the ice there heats up and releases gas, creating a jet. As the comet continues rotating, that spot moves into shadow and the jet shuts off, while a new jet might start somewhere else. This creates predictable patterns that astronomers can use to figure out how fast a comet is spinning and which direction its rotation axis points. 3I Atlas didn't follow these patterns. Instead of 1 or 2 distinct jets, Webb saw gas streaming away from multiple locations all over the object's surface. The gas release seemed almost random, not tied to any clear rotation pattern. Scientists tried to explain this by suggesting the object might be tumbling chaotically rather than spinning smoothly. Chaotic tumbling can happen when an object is irregularly shaped or when pieces break off unevenly, changing the object's balance. But even chaotic tumbling should produce some kind of pattern over time. The gas release from 3I Atlas looked almost like the object was being heated from the inside, not just by sunlight hitting its surface. This observation led to a radical question. Could 3I Atlas contain its own internal heat source? In our solar system, only a few objects generate significant internal heat. Large planets like Jupiter produce heat from their formation, still releasing energy from when they first collapsed together billions of years ago. Some moons, like Jupiter's moon Io, generate heat through tidal forces as their parent planet's gravity squeezes and stretches them. But small objects like comets and asteroids don't have any heat source beyond sunlight. They're too small to have retained heat from their formation, and they don't experience strong tidal forces. Yet the evidence from Webb suggested that 3I Atlas was somehow warm from within. One possibility was radioactive decay. Some isotopes of elements are unstable and break down over time, releasing energy in the process. This radioactive decay produces heat. Earth's interior is partly heated by radioactive decay of elements like uranium and thorium in the rocks deep underground. Could 3I Atlas contain enough radioactive material to heat it from inside? For a small object, you would need a very high concentration of radioactive elements to produce noticeable heat. Such high concentrations don't occur naturally in normal cosmic material. Scientists couldn't think of any natural process that would create a small, icy object loaded with radioactive elements. The idea seemed far-fetched, but it was hard to find better explanations. Another mystery was the object's changing brightness. Astronomers measuring 3I Atlas from night to night noticed that its brightness varied significantly. All rotating objects show some brightness variation because different parts of their surface reflect light differently. If you watch an asteroid through a telescope over several hours, you'll see it get brighter and dimmer as it rotates, and different sides face Earth. By timing these brightness changes, you can figure out how fast the object is rotating. Most asteroids complete one rotation every few hours. But 3I Atlas showed brightness changes that didn't fit a simple rotation pattern. The object would brighten suddenly, then fade, then brighten again at unpredictable times. Some of these brightness changes happened too quickly to be explained by rotation. An object would have to be spinning incredibly fast to cause brightness changes every few minutes, so fast that it would probably fly apart from centrifugal force. The only explanation that made sense was that pieces were actually breaking off 3I Atlas, exposing fresh, bright ice underneath and causing sudden increases in brightness. Webb's high-resolution images seemed to confirm this. The telescope captured what appeared to be small fragments trailing behind the main body of 3I Atlas. These fragments were releasing their own gas and dust, creating miniature comet tails. This was direct evidence that the object was falling apart as it traveled through our solar system. But the breakup raised more questions. If 3I Atlas was fragile enough to break apart from the gentle heating of our sun, how did it survive the journey through interstellar space? Space between the stars is not empty. There are hydrogen atoms, dust grains, and even larger particles floating in the void. An object traveling at the tremendous speeds needed to cross interstellar distances would collide with this material constantly. Those collisions should erode and destroy a fragile object over time. The journey from the nearest star to our sun would take tens of thousands of years, even at the incredible speeds 3I Atlas was traveling. During that time, the object would experience countless collisions with interstellar material. It would be bombarded by cosmic rays, high-energy particles that could penetrate deep into the object's structure and alter its chemistry. It would be exposed to the harsh radiation of space without any protection. For a delicate, loosely bound object to survive this journey intact seemed nearly impossible. Some scientists proposed that 3I Atlas might have been ejected from its home star system relatively recently, perhaps just thousands of years ago rather than millions of years ago. If the journey was shorter, the object would have experienced less damage from space weathering. But this created a new puzzle. For Earth to happen to detect 3I Atlas during the tiny window of time between when it was ejected and when it would have been destroyed suggested remarkable luck. The odds of catching such an object at just the right moment seemed incredibly low. Another possibility was that 3I Atlas formed differently than objects in our solar system. Perhaps in other star systems, objects can form with structures and compositions that we never see here. Our solar system formed from a rotating disk of gas and dust around the young sun. As particles in this disk collided and stuck together, they gradually built up larger and larger objects. The process was slow and gentle at first, but as objects grew bigger, their gravity became stronger, and they could attract material more quickly. Eventually, this process formed planets, moons, asteroids, and comets. But not all star systems form the same way. Some stars form in dense clusters where they can gravitationally interact with each other. These interactions can stir up the disks of material around young stars, sending objects flying in all directions. Some might escape entirely and begin wandering through interstellar space. If these ejected objects formed in a different environment than our solar system's objects, they might have different properties. Perhaps the star system where 3I Atlas formed had unusual amounts of certain elements, leading to objects with strange compositions. Webb's spectroscopic data provided clues about where 3I Atlas might have come from. By measuring the exact wavelengths of light absorbed by different molecules in the gas, scientists could determine the isotope ratios of elements like hydrogen, carbon, and oxygen. Isotopes are versions of an element that have different numbers of neutrons in their nucleus. For example, most hydrogen has 1 proton and no neutrons, but a rare form called deuterium has 1 proton and 1 neutron. The ratio of normal hydrogen to deuterium in an object tells us about the conditions where that object formed. The deuterium to hydrogen ratio in 3I Atlas was different from what we see in solar system comets. It was higher, suggesting that 3I Atlas formed in a colder environment than our comets did. This made sense if 3I Atlas came from a star system farther from the galactic center, where temperatures are generally lower. Our sun orbits about halfway out from the center of the Milky Way galaxy. Stars farther out orbit in a colder region of space. If 3I Atlas came from a star in the outer galaxy, it would have formed in colder conditions, which could explain the high deuterium ratio. But the isotope ratios raised another mystery. Some ratios matched expectations for a cold formation environment, but others didn't. The ratio of carbon-12 to carbon-13 was different from any solar system object, suggesting exposure to intense radiation at some point in the object's history. The ratio of oxygen-16 to oxygen-17 was also unusual. These inconsistencies hinted at a complex history. Perhaps 3I Atlas didn't form in a simple, straightforward way. Maybe it experienced multiple events that altered its chemistry over time. One radical idea was that 3I Atlas might have passed close to another star during its journey through space. If it flew near a star, the intense radiation and heat could have altered the object's surface chemistry. Some isotopes can be destroyed by radiation, while others are created, changing the ratios we observe. But for this to happen, 3I Atlas would have had to pass very close to a star, close enough to be heated significantly, but not so close that it was destroyed. The probability of such a close encounter seemed very low. Space is vast and stars are far apart. The chance of an interstellar object randomly passing close enough to a star to be affected seemed unlikely. Webb also detected something else unexpected in its observations. The coma, the cloud of gas and dust surrounding 3I Atlas, showed layered structure. When Webb looked at the coma in different wavelengths of infrared light, it saw distinct shells or layers of material at different distances from the object's nucleus. These shells suggested that 3I Atlas had experienced multiple episodes of activity, each one releasing a burst of gas that expanded outward in a shell. As new shells formed, older shells moved farther out, creating the layered pattern Webb observed. This kind of episodic activity is rare, but not unknown in solar system comets. Sometimes a pocket of ice deep inside a comet suddenly gets exposed, perhaps when an overlying layer collapses. The exposed ice rapidly sublimates, releasing a burst of gas. These outbursts can briefly make a comet much brighter and more active. But the outbursts from 3I Atlas seemed more frequent and more regular than those seen in solar system comets. It was as if something was triggering periodic bursts of activity, something internal to the object rather than external heating from the sun. Could 3I Atlas be rotating in such a way that internal stress built up and released periodically? Imagine a ball of ice and rock held together weakly, spinning as it travels through space. As it spins, centrifugal force tries to throw pieces outward. If the object is spinning slowly, gravity and friction hold it together. But if something speeds up the rotation, perhaps a chunk breaking off asymmetrically, the increased centrifugal force could overcome the weak bonds holding the object together. Parts of the surface could crack and collapse, releasing pockets of ice that immediately sublimate. This release of gas could then change the object's spin again, setting up another cycle. Webb's thermal imaging revealed temperature differences across the surface of 3I Atlas that supported this idea. Some parts of the object were significantly warmer than others, even parts that should have been receiving the same amount of sunlight. If the object was cracking and exposing fresh material, those areas would show temperature anomalies. Fresh ice sublimating would cool the surface through evaporation, while areas where gas was venting from inside might be warmer. The temperature map of 3I Atlas looked patchy and irregular, unlike the smooth temperature gradients seen on normal comets. The size and shape of 3I Atlas also remained uncertain despite Webb's observations. The object was surrounded by so much gas and dust that its true nucleus was hard to see. Scientists estimated it was somewhere between a few hundred meters and a few kilometers across. But the uncertainty was large. Attempts to measure its shape from brightness variations were complicated by the irregular brightening and fading caused by breakup. The object might be spherical, elongated, or completely irregular. Without knowing its shape, scientists couldn't accurately calculate its mass or density, which made understanding its composition even harder. One thing Webb's observations made clear was that 3I Atlas was losing mass rapidly. The amount of gas and dust it was releasing would strip away a significant fraction of its total mass during its passage through the inner solar system. If the object continued at this rate, it might not survive to exit our solar system. Instead, it could completely disintegrate, breaking into smaller and smaller pieces until nothing recognizable remained. This raised a poignant possibility. We might be watching the death of an interstellar traveler, an object that journeyed across light years of space only to be destroyed during its brief passage through our small corner of the galaxy. The rapid mass loss also meant that 3I Atlas looked very different now than it did when it entered our solar system. The object we were observing was already significantly smaller and lighter than the object that crossed the outer edges of our solar system months earlier. Any observations we made were snapshots of a dying object in its final days, not measurements of its original state. This complicated efforts to understand where it came from and what it was made of. We were trying to reconstruct the history of an object that was actively destroying itself before our eyes. Scientists debated whether the breakup was triggered by our sun's heat or whether 3I Atlas was already disintegrating before it arrived. Perhaps the object was damaged during its interstellar journey and was barely holding together when it entered our solar system. The sun's gentle heating might have been the final stress that pushed it over the edge into collapse. If this was true, then 3I Atlas might not be representative of typical interstellar objects. We might be seeing an unusual case, an object that was already dying rather than a healthy example of what travels between the stars. Alternatively, maybe all interstellar objects are fragile and most of them completely disintegrate before anyone notices them. Perhaps 3I Atlas and ʻOumuamua are not special. They might be typical examples, and we only notice them because they survived long enough to get close to the sun where our telescopes could spot them. Countless other interstellar visitors might pass through the outer solar system undetected because they never come close enough to warm up and become visible. This was a sobering thought. We might be missing most interstellar objects because our detection methods can only find ones that survive the trip to the inner solar system. Webb's discovery of complex organic molecules in such abundance around 3I Atlas sparked intense interest among astrobiologists. These scientists study the possibility of life elsewhere in the universe. They know that life as we understand it requires certain chemical building blocks, particularly complex carbon-based molecules. Finding these molecules in space is not unusual, but finding them in such high concentrations was remarkable. It suggested that whatever star system 3I Atlas came from had chemistry conducive to forming complex organic compounds. If those conditions existed there, they might exist around many stars. The building blocks of life might be common throughout the galaxy. Some researchers wondered whether 3I Atlas could actually be carrying living organisms or the remnants of life. This idea, called panspermia, suggests that life might spread between star systems on rocks and ice traveling through space. If a planet hosting life gets hit by a large asteroid, the impact could blast pieces of the planet into space. Some of these pieces might escape the planet's gravity entirely and wander through the galaxy. If they eventually land on another planet, they could potentially seed it with life. The idea is controversial because space is harsh. Microorganisms would have to survive intense radiation, extreme cold, and the vacuum of space for potentially millions of years. Most scientists think this is unlikely, though not impossible. Webb searched for any signs of biological activity in the gas from 3I Atlas. Living things produce specific combinations of molecules that are hard to create through purely chemical processes. For example, the presence of oxygen and methane together is a strong hint of biology because these molecules react with each other chemically. If you find them together, something must be constantly producing them to replace what's being destroyed. By reactions, on Earth, plants produce oxygen through photosynthesis, while microbes in swamps and cow stomachs produce methane. Finding both gases together in an atmosphere is a sign that life might be present. Webb didn't find clear evidence of biological activity in 3I Atlas, but the data wasn't conclusive. The object was releasing so many different chemicals in such a chaotic way that teasing out meaningful patterns was difficult. Some combinations of molecules were intriguing but could be explained through non-biological chemistry. The intense radiation in space can drive chemical reactions that create complex organic molecules without any life involved. Disappointing as it was, scientists couldn't claim that 3I Atlas showed signs of life. The most they could say was that it showed the star system it came from had interesting chemistry. The trajectory of 3I Atlas provided another fascinating puzzle. By tracking its path backward in time, astronomers tried to figure out where it came from. They calculated the object's motion, accounting for the gravity of the sun, planets, and even the slight push from gas venting off its surface. Working backward, they could trace where 3I Atlas was millions of years ago. The calculations pointed toward a region of space in the direction of the constellation Camelopardalis. But pinpointing the exact star it came from was impossible. The object had been traveling for so long that small uncertainties in its current speed and direction became huge uncertainties when projected backward over millions of years. There were dozens of stars in the general direction 3I Atlas came from, any of which could have been its origin. Some were young stars still surrounded by disks of planet-forming material. Objects ejected from these systems would be fresh and relatively pristine. Other stars were old, their planetary systems long since settled. Objects from these systems would be ancient, perhaps billions of years old. Without knowing which star 3I Atlas came from, scientists couldn't determine the object's age or formation history. It was frustrating to have this visitor from another star system right in front of us, but be unable to figure out exactly where it came from. Some researchers suggested that 3I Atlas might not have come from any particular star at all. Perhaps it was a rogue object, ejected from its birth system so long ago that the connection was lost. Rogue planets and rogue asteroids are thought to exist, wandering through the galaxy unbound to any star. They were born in star systems but were kicked out through gravitational interactions. Once ejected, they travel alone through the darkness of interstellar space. If 3I Atlas was a rogue, it might have been wandering for billions of years, long enough that the star it formed around has moved far away. The galaxy rotates and stars don't stay in one place. Over billions of years, a star can move to a completely different part of the galaxy. Tracing 3I Atlas back to its origin would be impossible if it was truly ancient. The amount of data Webb collected on 3I Atlas was enormous. Every observation session produced gigabytes of information. The telescope captured images at dozens of different infrared wavelengths. It recorded spectra showing absorption and emission lines from hundreds of different molecules. It measured temperatures, brightnesses, and positions with incredible precision. All of this data needed to be analyzed carefully by scientists around the world. Different research groups focused on different aspects of the observations, trying to piece together a complete picture of what 3I Atlas was and where it came from. As data analysis continued, new mysteries emerged faster than old ones were solved. Every answer seemed to raise two new questions. Scientists found themselves both excited and frustrated. Excited because they were gathering unprecedented data about an interstellar object. Frustrated because the object refused to fit into neat categories. It wasn't quite like a comet, not quite like an asteroid, and not quite like anything else they had seen before. 3I Atlas was forcing astronomers to expand their thinking about what kinds of objects exist in the galaxy. Some of the most interesting data came from comparing 3I Atlas to ʻOumuamua, the first confirmed interstellar object. ʻOumuamua was different in almost every way. It showed no visible gas release, at least not at levels we could detect. Its brightness variation suggested an elongated shape, possibly cigar-shaped or pancake-shaped. Its motion showed a slight acceleration away from the sun that couldn't be explained by gravity alone. Scientists argued intensely about what caused this acceleration. Some said it was gas venting from the surface, too faint to see but strong enough to push the object. Others proposed exotic explanations like light pressure on a thin, reflective surface, or even alien technology. The debate was never fully resolved before ʻOumuamua disappeared from view. 3I Atlas was different. It clearly was venting gas, lots of it. Its brightness changes seemed chaotic rather than regular. Its trajectory showed acceleration too, but this acceleration could be explained by the obvious gas jets pushing on the object. In many ways, 3I Atlas was easier to understand than ʻOumuamua. It behaved more like a familiar comet, even if its composition and activity patterns were unusual. This was both reassuring and disappointing. Scientists had hoped that studying more interstellar objects would reveal patterns and similarities. Instead, each interstellar visitor seemed to be unique, adding to the confusion rather than resolving it. The differences between ʻOumuamua and 3I Atlas might tell us something important about the diversity of objects in the galaxy. Our solar system contains icy comets and rocky asteroids, along with objects that are mixtures of both. Moons, dwarf planets, and countless smaller bodies all have different compositions and histories. If our solar system is this diverse, other star systems must be even more so. Different stars form with different mixtures of elements. Different planets can alter the chemistry of material in a system through their gravity and heat. The variety of objects wandering between the stars might be enormous, far greater than what we see in our own stellar neighborhood. This diversity made some scientists wonder if we would ever find typical interstellar objects. Perhaps there is no such thing as typical. Maybe every object is unique, shaped by the particular conditions in its home system and by its experiences during millions of years of interstellar travel. If so, we might need to observe hundreds or thousands of interstellar visitors before we could start to draw general conclusions. With current technology, we detect maybe one interstellar object every few years. At that rate, understanding the population of objects between the stars would take centuries. Webb's observations of 3I Atlas might represent one of the few chances we get to study an interstellar object in such detail. The next visitor might not arrive for years, and when it does, it might pass too quickly for detailed study or might not come close enough to the sun to be observed well. Scientists are making the most of this opportunity, extracting every bit of information they can from the data. They're developing new analysis techniques and building better computer models to interpret what they're seeing. The hope is that by thoroughly understanding 3I Atlas, they'll be better prepared to study the next interstellar visitor when it arrives. Some researchers are already planning future missions to intercept interstellar objects. The idea would be to launch a spacecraft that could rendezvous with an interstellar visitor as it passes through our solar system. Getting close to the object would allow much more detailed study than is possible with telescopes. A spacecraft could measure the object's composition directly, collect samples of gas and dust, or even land on the surface. The main challenge is speed. Interstellar objects are moving very fast. Matching their velocity would require a spacecraft with powerful engines or clever use of planetary gravity assists. Several mission concepts have been proposed, but none have been funded yet. The hope is that as more interstellar objects are discovered, interest and funding for such missions will grow. One proposed mission would use a network of small, fast probes deployed throughout the solar system. When an interstellar object is detected, the closest probe would activate and attempt to intercept it. The probe wouldn't necessarily land or match velocity. Instead, it might just perform a fast flyby, taking pictures and measurements during a few brief moments as it zipped past. Even a flyby would provide far better data than telescope observations. The spacecraft could get much closer and could observe parts of the object that are always in shadow when viewed from Earth. Multiple probes stationed at different locations would increase the chances that at least one would be positioned to intercept any given interstellar visitor. The discovery of 3I Atlas and the detailed observations by Webb have energized the field of interstellar object studies. What was once a purely theoretical topic has become an active area of research. Scientists now know that interstellar objects are real, They visit our solar system occasionally, and they can be studied if we're quick and lucky. This knowledge is driving the development of better detection systems, new analysis methods, and plans for future missions. The field is evolving rapidly, and each new discovery adds to our understanding while also revealing new mysteries. Webb's observations also demonstrated the power of infrared astronomy for studying small solar system bodies. Many asteroids and comets are too faint or too far away for traditional visible light telescopes to study in detail, but they emit infrared light from their own heat, which Webb can detect. This makes Webb an invaluable tool for studying not just interstellar visitors, but also objects from our own solar system. Astronomers are using Webb to study distant Kuiper Belt objects, asteroids in the main belt, and comets from the Oort cloud. Each observation reveals new details about the diversity of small bodies in our cosmic neighborhood. The technological achievement represented by Webb cannot be overstated. Building a telescope that can operate at -200 degrees Celsius, fold up to fit inside, a rocket, unfold perfectly in space, and maintain precise alignment of 18 separate mirror segments is an engineering marvel. The fact that it works at all is amazing. The fact that it works so well is extraordinary. Webb is providing data quality that exceeds what scientists hoped for when they designed it decades ago. The telescope is expected to operate for at least 10 years, possibly much longer. During that time, it will make countless discoveries, transforming our understanding of the universe. For 3I Atlas specifically, Webb's observations are providing a wealth of data that will keep scientists busy for years. The raw data has been released to the scientific community, and researchers around the world are analyzing it using different techniques and asking different questions. Some are focused on the object's composition, trying to identify every molecule in the gas and dust. Others are studying the dynamics of the breakup, modeling how the object is falling apart and trying to predict what will happen next. Still others are comparing 3I Atlas to solar system comets, looking for similarities and differences that might reveal something about how objects form around different stars. One particularly interesting analysis involves looking at the dust released by 3I Atlas. Dust grains in space are tiny, typically smaller than a micrometer across. They're made of various materials including silicates, carbon compounds, and ices. When light hits these grains, some of it scatters and some is absorbed. By measuring how light scatters at different wavelengths, scientists can determine what the dust is made of and how big the grains are. Webb's infrared observations are perfect for this kind of analysis because different materials have distinct infrared signatures. The dust from 3I Atlas shows an unusual composition. It contains the expected silicate materials that make up most cosmic dust, but also significant amounts of organic materials. Some of these organics are simple, like methane ice, but others are complex chains and rings of carbon atoms. These complex organics are sometimes called tholins, a term that covers a wide range of organic compounds produced by radiation acting on simpler molecules. Tholins are found on some moons in our solar system, particularly on Saturn's moon Titan. They give Titan its orange color. Finding abundant tholins in 3I Atlas suggests that the object or its parent material was exposed to significant radiation at some point. The size distribution of dust grains also revealed something interesting. Most comets produce a mix of grain sizes, from microscopic particles up to chunks several centimeters across. The smallest grains are pushed away from the sun by light pressure, while larger chunks follow more ballistic trajectories. By measuring how fast different dust particles move away from 3I Atlas, scientists could estimate their sizes. The data showed an unusual abundance of very small grains, much smaller than what typical comets produce. This might indicate that 3I Atlas material is particularly fragile, breaking into tiny pieces easily. Or it might mean that some process is shattering dust grains after they're released, perhaps solar radiation breaking apart delicate organic compounds. As 3I Atlas continues its journey outward from the sun, it will gradually fade from view. The farther it gets, the less sunlight it receives, so less ice will sublimate and less gas will be released. The object will become dimmer and harder to see. Eventually, it will pass beyond the range where even Webb can detect it. At that point, our detailed observations will end. The object will continue traveling into the depths of interstellar space, perhaps eventually encountering another star system billions of years from now. We'll never know what happens to it after it leaves our sight. The brief window when 3I Atlas was visible and close enough for detailed study represents a fleeting opportunity. In cosmic terms, the object's passage through our solar system lasts mere moments. We're fortunate to have the technology to study it during this brief time. A century ago, we wouldn't have had telescopes powerful enough to detect 3I Atlas at all. Even a few decades ago, our instruments wouldn't have been able to measure its composition or observe its breakup in detail. We're living in a special time when our technology has finally reached the level needed to study interstellar visitors. But we're also at the beginning of this capability. Future telescopes will be even better, able to detect fainter objects and measure them more precisely. Plans are already underway for next-generation telescopes that will succeed Webb. These future observatories will have even larger mirrors and more sensitive detectors. They'll be able to study interstellar objects at greater distances and in more detail. Some will operate in space like Webb. Others will be ground-based telescopes with enormous mirrors 30 meters or more in diameter. Together, these future facilities will allow astronomers to study not just the occasional interstellar visitor that comes close to the Sun, but also objects passing through the outer solar system. This will give us a much better census of what's traveling between the stars. One of the key questions these future observations will address is how common interstellar objects really are. Right now, we've only detected a handful because our surveys aren't sensitive enough to find most of them. Calculations based on the few we've found suggest there might be thousands of interstellar objects in our solar system at any given time, most of them too far away or too small to detect. Better telescopes will allow us to find more of these objects and get a better estimate of their true abundance. This number will tell us important things about how planetary systems evolve and how many objects get ejected into interstellar space during planet formation. The study of 3I Atlas has also highlighted gaps in our theoretical understanding. Before detecting interstellar objects, scientists had models of what they expected to find. These models were based on computer simulations of planetary system formation and evolution. The simulations showed that young planetary systems should eject large numbers of small bodies during their early history. As planets form and migrate, their gravity stirs up remaining material, flinging some of it into interstellar space. The models predicted that the galaxy should be filled with these ejected objects wandering between the stars. But the models didn't make detailed predictions about what these objects would look like or what they'd be made of. Now that we're finding interstellar objects, we can compare them to the predictions and refine our models. 3I, Atlas, and ʻOumuamua are providing crucial test cases. Scientists can adjust their simulations to match what we observe, then use the refined models to predict what else we might find. This iterative process of observation, modeling, and prediction is how science advances. Each new discovery forces us to update our understanding. The updated understanding leads to new predictions, which drive new observations. The cycle continues, gradually bringing our models closer to reality. Some of the biggest mysteries surrounding 3I Atlas may never be fully resolved. We may never know exactly which star it came from or how old it is. We may never understand why it's breaking apart in such a dramatic fashion or what caused its unusual composition. Science often works this way. We get tantalizing hints and partial answers, but complete certainty remains elusive. Future discoveries might provide context that helps us better understand 3I Atlas. Or the object might remain an enigma, a strange visitor whose secrets died with it as it disintegrated. What we do know is that 3I Atlas has expanded our understanding of what exists in the galaxy. It has shown us that objects can travel between stars carrying complex chemistry with them. It has demonstrated that interstellar objects can be fragile and dynamic, changing as they journey through space. It has revealed the power of instruments like Webb to study these fleeting visitors. And it has raised profound questions about the diversity of material in the galaxy and the processes that create such diversity. The molecules detected in 3I Atlas gas have particular significance for understanding the chemistry of other star systems. Every star forms from a cloud of gas and dust with a particular chemical composition. This composition depends on the star's location in the galaxy when it formed, and what previous generations of stars enriched the region with heavy elements. The planets, asteroids, and comets that form around a star inherit this chemistry. By Studying an interstellar object, we're getting a sample of material from another star system. A direct measurement of chemistry we usually can only infer from distant observations. The carbon-to-oxygen ratio in 3I Atlas was particularly interesting to scientists. This ratio varies from star to star and affects what kinds of planets and objects can form. A high carbon-to-oxygen ratio favors the formation of carbon-rich compounds like graphite and silicon carbide. A low ratio favors silicate minerals and water ice. Our solar system has a particular carbon-to-oxygen ratio that led to the rocky planets and icy comets we see. The ratio in 3I Atlas was different, suggesting it formed in a system with a different elemental composition. This tells us that the variety of planetary systems in the galaxy is even greater than we imagined. Understanding this chemical diversity is crucial for astrobiology. Life as we know it requires certain elements in certain proportions. Too much of one element or too little of another might make life difficult or impossible. By studying the chemistry of interstellar objects, we learn about the range of conditions that exist around other stars. This helps us estimate how many star systems might be suitable for life. If we find that most systems have chemistry very different from ours, it might mean life is rare. If we find chemistry similar to our solar system is common, it would support the idea that life might be widespread. The organic molecules in 3I Atlas are particularly relevant to this question. These molecules are the building blocks from which life could potentially emerge. Finding them in abundance on an interstellar object suggests they're common in the galaxy. This is good news for the possibility of life elsewhere. It means the raw materials needed for life exist throughout the galaxy, carried on countless objects traveling between the stars. Some of these objects will eventually fall onto planets. If the conditions on those planets are right, the delivered organic molecules might contribute to the emergence of life. This connects to theories about how life began on Earth. Scientists know that Earth was bombarded by asteroids and comets during its early history. Some of these impactors likely delivered water and organic molecules to our planet. Whether this delivery was essential for life's origin or merely supplemental remains debated. But the fact that impacts can deliver complex chemistry is well established. If similar processes happen on planets around other stars, and if interstellar objects like 3I Atlas are common, then the ingredients for life might be distributed widely through the galaxy. This doesn't guarantee life exists elsewhere, but it makes the possibility more plausible. The dramatic breakup of 3I Atlas also teaches us about the ultimate fate of small bodies in space. Most asteroids and comets will eventually be destroyed through collisions, gravitational disruption, or gradual erosion. But watching an object actively disintegrate before our eyes is rare. Usually these events happen too far away or too quickly for us to observe in detail. 3I Atlas gave scientists a front-row seat to destruction, allowing detailed study of how an icy object falls apart. This observational data can be compared to computer models of breakup processes, helping to refine those models. Better models will help us understand the life cycle of small bodies throughout the galaxy. The forces causing 3I Atlas to break apart are subtle but powerful. Thermal stress is one factor. As parts of the object heat up in sunlight and cool down in shadow, the material expands and contracts. Over time, this repeated expansion and contraction can create cracks. Once cracks form, they can propagate through the object, eventually splitting it into pieces. Rotational stress is another factor. If the object is spinning, centrifugal force tries to throw material outward. For a loosely bound object, even slow rotation can create stress. If cracks weaken the structure, rotation can pull the pieces apart. Gas pressure from sublimating ice adds another stress. As ice deep inside 3I Atlas turns to gas, the gas needs to escape. It percolates through cracks and pores in the structure, creating pressure. This pressure can enlarge existing cracks and create new ones. In extreme cases, pressure buildup can cause explosive outbursts, blowing chunks of material off the surface. Webb may have captured some of these outbursts in action, though distinguishing them from normal gas release is challenging. All these stresses work together, gradually weakening the object until it can no longer hold together. Understanding these breakup processes has practical applications beyond pure science. As humanity considers missions to asteroids and comets, knowing how these objects respond to stress becomes important. If we want to land a spacecraft on an asteroid or extract resources from it, we need to know if the object is solid or fragile. A fragile object might not support a landing or might break apart if we try to mine it. The lessons learned from studying 3I Atlas will inform future mission planning and engineering. They'll help us design spacecraft and procedures that can work with the reality of fragile, loosely bound objects. The observation campaign for 3I Atlas involved coordination between many telescopes and research teams. Webb was just one player, albeit an important one. Ground-based telescopes tracked the object continuously, monitoring its brightness and position. Radio telescopes searched for emissions from certain molecules. Ultraviolet telescopes studied the outer parts of the coma where lightweight atoms are most abundant. Each telescope provided a piece of the puzzle. Combining all the observations together gave a more complete picture than any single instrument could provide alone. This kind of coordinated multi-wavelength astronomy is becoming standard for studying interesting objects. It maximizes the scientific return by bringing different capabilities to bear on the same target. The international nature of these observations is worth noting. Telescopes from North America, Europe, Asia, and South America all participated. Scientists from dozens of countries collaborated on the data analysis. Space science is one of the most international of all scientific endeavors. Objects in space don't belong to any one nation. They're humanity's common heritage. The spirit of cooperation and shared discovery that characterizes space science is one of its most inspiring aspects. Researchers who might otherwise never interact work together toward common goals. The study of 3I Atlas brought together expertise in observational astronomy, theoretical modeling, laboratory chemistry, and planetary science from around the world. This collaborative approach will become even more important as we discover more interstellar objects. Each one will require rapid response and coordinated observation. Networks of automated telescopes are being developed specifically to detect and track such objects. When an interstellar visitor is spotted, these networks can immediately notify the astronomical community. Pre-planned observation campaigns can swing into action within hours. Webb and other major telescopes can be scheduled for target of opportunity observations, interrupting their regular programs to observe something new and exciting. This rapid response capability will be crucial for studying objects that might pass through our solar system in just a few months. The scientific papers published about 3I Atlas will number in the dozens or perhaps hundreds. Each paper will focus on a different aspect of the observations and analysis. Some will present basic data like the object's position and brightness over time. Others will offer interpretations and models attempting to explain what was observed. Still others will compare 3I Atlas to other objects, looking for patterns and relationships. The body of literature will grow over several years as different research groups complete their analyses. This accumulated knowledge will form the foundation for our understanding of this particular object and interstellar visitors in general. Students and early career scientists working on 3I Atlas data will gain valuable experience that will serve them throughout their careers. Many will become the next generation of experts in cometary science, interstellar studies, and infrared astronomy. The observation of 3I Atlas is not just advancing our current understanding, but also training future researchers. This educational aspect of major observing campaigns is sometimes overlooked, but is crucial for the long-term health of the field. New generations of scientists need opportunities to work with cutting-edge data and tackle challenging problems. 3I Atlas provides exactly that kind of opportunity. Public interest in interstellar objects is significant. Stories about ʻOumuamua captured popular imagination, with media coverage and public speculation about its origin and nature. 3I Atlas has generated similar interest. People find the idea of a visitor from another star system intrinsically fascinating. It connects to deep human questions about whether we're alone in the universe and what else might be out there. Scientists working on 3I Atlas have made efforts to communicate their findings to the public through press releases, articles, and social media. Making science accessible and engaging to non-specialists is an important part of modern research. It helps justify public funding for expensive instruments like Webb and maintains enthusiasm for space exploration. Some of the most compelling images from Webb show 3I Atlas surrounded by its glowing coma. The false color images, where different infrared wavelengths are mapped to visible colors we can see, reveal structures invisible to our eyes, Shells and streamers of gas glow in reds and oranges. Dust reflects sunlight in blues and greens. The nucleus of the object, when visible through the surrounding material, appears as a bright point at the center. These images are not just scientifically valuable, but also aesthetically beautiful. They remind us that the universe is full of wonders and that studying space reveals both knowledge and beauty. As 3i Atlas fades from view, attention will turn to the next interstellar visitor. Surveys are constantly scanning the sky, looking for objects with unusual trajectories. Each year, tens of thousands of new asteroids are discovered. Most are ordinary members of our solar system. But every so often, something unusual appears. Its orbit doesn't fit the pattern. Its speed is wrong. Its direction is unexpected. These are the clues that astronomers look for when searching for interstellar visitors. Improved detection methods mean we're likely to find more such objects in coming years, perhaps one every year or two instead of one every few years. Each discovery will add to our knowledge and might spring surprises we never anticipated. The legacy of 3i Atlas will extend far beyond the object itself. The techniques developed to study it will be applied to future interstellar visitors. The questions it raised will motivate new research. The data it provided will be analyzed and reanalyzed as new methods and ideas emerge. In some ways, the scientific investigation of 3i Atlas is just beginning. Years from now, researchers will still be mining the Webb observations for insights. New theories will be tested against the data. Unexpected connections will be made. This is the nature of rich data sets. They continue providing value long after the observations themselves are complete. So what is 3i Atlas hiding? The answer is complex. It's hiding clues about another star system and its composition. It's hiding information about the journey between stars and its structure. It's hiding evidence of processes we don't fully understand in its behavior. And perhaps it's hiding answers to questions we haven't yet learned to ask. Every time humanity gains new capabilities to study the universe, we discover things we never expected. Webb's observation of 3i Atlas is one example of this pattern. We pointed our most powerful infrared telescope at an interstellar visitor and found it was stranger and more complex than we imagined. The universe continues to surprise us, and that's exactly how it should be. If everything matched our predictions, it would mean we already understood everything, and there would be nothing left to discover. The fact that 3i Atlas confounds some of our expectations is exciting, not disappointing. It means there's still mystery in the universe. There are still phenomena we need to figure out. There are still discoveries waiting to be made. And we have the tools and the knowledge to pursue those discoveries. As humanity looks to the future, the study of interstellar objects will become an established part of astronomy. What is now novel and exciting will become routine. We'll catalog interstellar visitors the way we now catalog asteroids and comets from our own solar system. We'll measure their properties, track their orbits, and compare them to each other. We might even launch missions to visit them up close. All of this seemed like science fiction just a few years ago. Now it's rapidly becoming reality. The arrival of 3i Atlas and the detailed observations by Webb mark a turning point in our relationship with the galaxy. We're no longer confined to studying just our own solar system. We can now reach out and study material from other star systems, samples of the broader galactic environment delivered right to our doorstep. This expanding scope of astronomy fills the future with promise. Every interstellar object teaches us something new. Every observation refines our understanding. Every discovery pushes the boundaries of knowledge a little farther. The story of 3i Atlas is one chapter in a much larger story, the story of humanity learning about its place in the cosmos. We started by understanding our planet, then our solar system, then nearby stars, and now the galaxy itself is becoming our laboratory. Objects like 3i Atlas are messengers from that larger realm, bringing information from places our spacecraft may never reach. By studying these messengers carefully, we can learn about distant environments without ever leaving our own cosmic neighborhood. The James Webb Space Telescope, with its incredible capabilities, is our window into this larger universe. Its observations of 3i Atlas demonstrate what's possible when we combine cutting-edge technology with scientific curiosity. The telescope will continue operating for many years, making countless more discoveries. It will study distant galaxies, nearby planets, forming stars, and dying stars. and occasionally it will turn its gaze on something unexpected like an interstellar visitor. These opportunistic observations often produce the most surprising results. They remind us that the universe is full of phenomena we haven't anticipated. Staying alert to the unexpected is just as important as following careful plans. The scientists analyzing Webb's data on 3I Atlas are engaged in detective work. They're trying to reconstruct the history of an object based on limited clues. They're inferring properties they can't measure directly from observations they can make. They're building models and testing them against reality. This process is painstaking and sometimes frustrating. Dead ends are common. Promising ideas turn out to be wrong. But occasionally, everything clicks into place. A pattern emerges from the chaos. An explanation accounts for multiple observations at once. These moments of insight make the hard work worthwhile. They represent genuine progress in understanding. The complete story of what 3I Atlas is hiding may take years or even decades to fully unfold. Some aspects might never be completely understood with certainty. But the effort to understand is valuable regardless of how complete the final answer turns out to be. In science, the journey is as important as the destination. The skills developed, the techniques refined, and the questions raised all have value beyond any single object of study. The researchers working on 3I Atlas today are becoming the experts who will study future interstellar visitors. The methods they develop will become standard tools used throughout astronomy. The insights they gain will inform our understanding of planetary system formation and evolution across the galaxy. Future historians of science will look back on this era as the time when humanity first began seriously studying objects from other star systems. 3I, Atlas, and ʻOumuamua are pioneers, the first of what will eventually be many. They're opening a new window on the galaxy, providing a new way to study star systems beyond our own. This expansion of humanity's observational reach represents progress in the truest sense. We're learning about things we couldn't study before. We're asking questions we couldn't ask before. And we're finding that reality is more interesting and complex than our theories predicted. The final word on 3I Atlas may not be written for many years. But what we know already is remarkable. We know it came from another star system, carrying chemistry from that distant place. We know it's breaking apart dramatically as it passes through our solar system, giving us a unique opportunity to study its internal structure. We know it contains abundant organic molecules, suggesting the building blocks of life are common in the galaxy. And we know that it's more complex and puzzling than simple models predicted, forcing us to expand our understanding. These insights are valuable additions to human knowledge. They represent genuine progress in our quest to understand the universe. And they're just the beginning of what we'll learn as more interstellar visitors are discovered and studied. The James Webb Space Telescope has proven its worth many times over through discoveries like this. Its observation of 3I Atlas showcases the telescope's unique capabilities and its importance for modern astronomy. As Webb continues its mission, it will undoubtedly make many more surprising discoveries. But the study of this interstellar visitor will remain one of the highlights, a moment when we got our closest look yet at material from another star system and found it was full of mysteries. This is what makes science exciting, not confirming what we already know, but discovering what we didn't expect. 3I Atlas delivered that discovery, and in doing so, reminded us that the universe is more wonderful than we can imagine. The depth of Webb's observations allowed scientists to probe details that would have been completely impossible just a decade ago. One of the most fascinating aspects was the ability to track how 3I Atlas changed over time. Webb didn't just take a single snapshot. It observed the object repeatedly over several weeks as it moved through our solar system. Each observation revealed new changes. The pattern of gas jets shifted. The brightness fluctuated in new ways. Fragments that appeared in one observation had moved or disappeared by the next observation. This time series data gave scientists something like a movie of the breakup process, showing how the object evolved day by day. Analyzing these changes revealed information about the structure of 3I Atlas. The way pieces broke off suggested that the object had a layered structure, like an onion. The outer layers were more fragile and came off first. As these layers peeled away, they exposed deeper material that had different properties. This deeper, Material was less volatile, meaning it didn't turn to gas as easily, but it still contained pockets of highly volatile ice that would suddenly burst out when exposed. This created the unpredictable pattern of brightness changes and gas release that made 3I Atlas so hard to understand. The layered structure makes sense when you think about how objects form in space. When dust and ice particles first come together to build a larger object, they don't mix perfectly. Some regions end up with more ice, others with more rock. Some areas get compressed more tightly, while others remain loose and porous. Over time, the outer surface gets weathered by radiation and impacts, creating a crust that's different from the interior. If 3I Atlas formed billions of years ago, it would have accumulated this kind of complex structure over its lifetime. The layers we're seeing might represent different eras in the object's history, each layer telling part of the story of where it's been and what it's experienced. Webb's spectroscopic capabilities allowed scientists to measure not just what molecules were present, but also their physical state. Were they solid ice, liquid droplets, or gas? Were they hot or cold? Were they moving slowly or quickly? This level of detail revealed that the gas around 3I Atlas wasn't uniform. Different regions had different temperatures and compositions. Near the nucleus, the gas was hot and dense, heated by direct sunlight and still accelerating away from the surface. Farther out, the gas had cooled and spread out, forming a more diffuse cloud. And in some directions, there were streams of cold gas moving much faster than expected, perhaps ejected by explosive outbursts from inside the object. The temperature measurements were particularly revealing. The surface of 3I Atlas that faced the sun reached temperatures around minus 150 degrees Celsius. That might sound cold, but it's actually warm enough for water ice to sublimate fairly quickly. For comparison, the surface of comets in our solar system reaches similar temperatures when they're at the same distance from the sun. But the shadowed side of 3I Atlas was much colder, perhaps minus 200 degrees Celsius or even colder. This huge temperature difference between day and night sides creates thermal stress. The warm material expands while the cold material contracts. Over time, this stress can cause cracks and fractures. Webb also measured the temperature of the dust around 3I Atlas. Dust doesn't stay at the same temperature as gas because it's solid and absorbs sunlight differently. The smallest dust particles, those just a fraction of a micrometer across, heat up quickly in sunlight and can reach temperatures much higher than the gas around them. These tiny grains glow brightly in infrared light, which is exactly what Webb detects. By measuring how bright they are at different wavelengths, scientists could determine both their temperature and their size. The data showed that 3I Atlas was producing an unusual amount of very small dust grains, consistent with fragile material shattering into tiny pieces. The velocity of material leaving 3I Atlas provided more clues about what was happening. Gas escaping from a comet's surface is pushed away by sublimation pressure. Water ice turning to gas creates outward pressure that pushes the gas away from the surface. The speed this gas reaches depends on the temperature. Hotter gas moves faster. For a typical comet, gas leaves the surface at about a few hundred meters per second. But Webb measured gas speeds around 3I Atlas that sometimes reached over 1 kilometer per second, much faster than normal. This suggested that something was accelerating the gas beyond just sublimation pressure. Perhaps explosive outbursts were launching gas at high speed, or perhaps internal pressure had built up and was venting forcefully through cracks. The dust particles were moving more slowly than the gas, as expected. Dust has mass and momentum, so it doesn't get accelerated as easily as lightweight gas molecules. But even the dust was moving faster than scientists predicted based on simple models. This might mean the gas was dragging dust along more efficiently than usual, or that the dust grains were smaller and lighter than average. Either way, it was another sign that 3I Atlas was behaving unusually compared to normal comets. Scientists also looked for evidence of larger chunks being ejected. When a comet breaks apart, it doesn't just release gas and fine dust. Sometimes it throws off boulder-sized pieces that travel along with the main nucleus for a while before drifting away or breaking apart themselves. These larger pieces are hard to detect because they don't reflect much light and they don't produce their own gas and dust. But Webb's sensitive detectors can sometimes spot them by the faint sunlight they reflect. The images showed several candidate chunks near 3I Atlas, though it was hard to be certain they were real fragments rather than dense clumps of dust. If these chunks were real, they told an important story about the breakup mechanism. Ejecting large pieces requires significant force. It's not enough to just heat the surface and sublimate ice. You need some kind of explosion or structural failure to throw boulders into space. This pointed to internal pressure buildup and sudden release as a key part of what was happening to 3I Atlas. Ice deep inside the object was turning to gas but couldn't escape immediately. The gas pressure built up until it exceeded the strength of the overlying material. Then the surface ruptured, gas burst out, and pieces were blown off. This explosive activity is rare but not unknown in comets. Some comets have undergone dramatic outbursts that temporarily increase their brightness by factors of 10 or even 100. These outbursts last for hours or days before fading. They're thought to be caused by exactly the mechanism described above, internal pressure finding a weak point and venting explosively. But most comets go through their entire lives without a major outburst. The fact that 3I Atlas seemed to be having repeated outbursts suggested its structure was particularly prone to this kind of activity. Perhaps the internal ice was unusually volatile, or perhaps the structure was so weak that even small pressure increases could cause ruptures. The composition of 3I Atlas provided more food for thought. The organic molecules detected by Webb included not just simple compounds, but also more complex species. Scientists identified methanol, a simple alcohol. They found formaldehyde, a compound famously used to preserve biological specimens. They detected hydrogen cyanide, a toxic compound that's nonetheless an important building block for more complex organic chemistry. And they found hints of even larger molecules, though these were at the limit of what Webb could detect clearly. All of these compounds are known to exist in comets from our solar system, but again, the abundance was unusual. 3I Atlas seemed to be richer in organic chemistry than typical comets. This might reflect the composition of the material from which it formed. Perhaps its parent star system had more carbon available, leading to objects with higher organic content. Or perhaps the conditions where 3I Atlas formed favored the creation of organic molecules over simpler ices. Temperature, pressure, and radiation levels all affect what kinds of molecules form and survive in space. The presence of hydrogen cyanide is particularly interesting from an astrobiological perspective. This molecule is toxic to most life forms on Earth, but it's also a crucial ingredient in theories about how life began. Laboratory experiments have shown that hydrogen cyanide can react to form amino acids, the building blocks of proteins. It can also form nucleotides, the building blocks of DNA and RNA. In the harsh environment of early Earth, before life existed, chemical reactions involving hydrogen cyanide might have created the first complex molecules that eventually led to living things. Finding abundant hydrogen cyanide on an interstellar object suggests these kinds of chemistry can happen in many places throughout the galaxy. Webb also detected sulfur-bearing compounds around 3I Atlas. Sulfur is less abundant in space than carbon, nitrogen, and oxygen, but it plays important roles in chemistry and biology. On Earth, many proteins contain sulfur atoms at key positions. Volcanic gases on Earth contain sulfur compounds, and some microbes can metabolize sulfur compounds for energy. The sulfur compounds around 3I Atlas included hydrogen sulfide, which smells like rotten eggs, and sulfur dioxide, a gas produced by volcanoes. The presence of these molecules suggested that wherever 3I Atlas formed, sulfur was available and got incorporated into the ice. The isotope ratios of sulfur provided additional clues. Different isotopes of an element have slightly different masses because they have different numbers of neutrons in their nuclei. These mass differences affect how the isotopes behave in chemical reactions. Lighter isotopes tend to react slightly faster than heavier ones. Over time, this leads to enrichment or depletion of certain isotopes, depending on what reactions occurred. By measuring the ratios of different sulfur isotopes in 3I Atlas, scientists could learn about the chemical history of its material. The ratios were different from those in solar system objects, consistent with the idea that 3I Atlas formed in a different environment. All of these chemical details painted a picture of an object that had a complex history. It wasn't just a simple ball of ice and rock. It was a mixture of many different materials that had formed under specific conditions and had been altered by subsequent processes. Some of the chemistry might reflect conditions in the disk of material around its parent star billions of years ago. Other chemical signatures might have been created by radiation exposure during the interstellar journey. Still others were being created right now as Webb watched through reactions driven by sunlight breaking apart and rearranging molecules. The way Webb's different instruments worked together on 3I Atlas was a masterclass in modern observational astronomy. The near-infrared camera took wide-field images showing the overall structure of the coma and tail. These images revealed the morphology, the shape, and distribution of material. The near-infrared spectrograph measured precise wavelengths of light, identifying specific molecules. This provided the composition. The mid-infrared instrument probed slightly longer wavelengths, perfect for measuring temperatures and studying dust. Each instrument added a piece to the puzzle. Combining all the data gave a much richer picture than any single instrument could provide alone. The data reduction and analysis required sophisticated software and significant computing power. Raw data from Webb isn't immediately useful. It needs to be processed to remove instrumental effects, calibrated against standard sources, and carefully analyzed to extract meaningful scientific results. This process takes time and expertise. Large teams of scientists and engineers work together to develop the necessary tools and techniques. For 3I Atlas, the data processing was particularly challenging because the object was moving and changing. Techniques designed for static sources had to be adapted for a dynamic, evolving target. One of the advantages of Webb's location at the second Lagrange point is that it can observe objects continuously for long periods without Earth or the Moon blocking the view. Ground-based telescopes can only observe at night, and even then, they can only see objects above the horizon. Weather can interrupt observations, but Webb, floating in space far from Earth, has much more flexible scheduling. It can track an object like 3I Atlas for hours or days without interruption, limited only by the need to occasionally point away to calibrate instruments or observe other targets. This continuous monitoring capability was crucial for capturing the dynamic changes in 3I Atlas. The scientific papers resulting from Webb's observations of 3I Atlas will contribute to multiple fields of research. Cometary scientists will use the data to refine models of comet structure and activity. Astrochemists will analyze the molecular detections to understand organic chemistry in space. Dynamicists will study the breakup process to learn about the strength and structure of small icy bodies. And theorists modeling planetary system formation will use constraints on 3I Atlas composition to understand conditions around other stars. Each research group will focus on different aspects of the data, extracting insights relevant to their particular questions. The observations also have implications for future space missions. If humanity ever wants to visit an interstellar object up close, we need to understand what we might encounter. Are these objects solid and stable, or fragile and prone to breaking apart? Can a spacecraft safely land on an interstellar visitor, or would the surface be too weak to support it? What kind of instruments would be most valuable for studying such an object? Webb's observations of 3I Atlas provide important information for answering these questions. They show that at least some interstellar objects are fragile and active, which would present both challenges and opportunities for a visiting spacecraft. The technological spin-offs from developing and operating Webb are also worth noting. Building a telescope that works at -230 degrees Celsius required innovations in materials science, cryogenic engineering, and precision manufacturing. These innovations have applications beyond astronomy. Medical imaging devices, industrial sensors, and military reconnaissance systems all benefit from advances in infrared detector technology. The computer algorithms developed to process and analyze Webb's data have applications in other fields where large amounts of complex data need to be understood, from medical diagnosis to financial analysis. The international collaboration that built and operates Webb involved space agencies and research institutions from the United States, Europe, and Canada. Thousands of people contributed to the project, over more than 2 decades of development. This kind of large-scale, long-term international cooperation on a scientific project is remarkable. It shows what humanity can achieve when we work together toward common goals. The success of Webb is not just a scientific achievement, but also a diplomatic and organizational one. It demonstrates that countries can cooperate effectively even when they have disagreements in other areas. The cost of Webb was substantial, about $10 billion over its lifetime from concept to launch and operation. Critics sometimes question whether such expensive projects are justified. But the scientific and technological returns from Webb are enormous. The discoveries it makes will fill textbooks for decades. The technologies it develops will enable future innovations. And the inspiration it provides to young people considering careers in science and engineering is immeasurable. When you calculate the cost per person, it works out to just a few dollars per year for each resident of the countries that funded it. That's less than the cost of a cup of coffee, and the return on investment includes expanding human knowledge about the universe. 3I Atlas also reminds us of how much we still don't know. For all our technological prowess and scientific understanding, we were surprised by this object. It didn't behave the way our models predicted. Its composition was unusual. Its activity pattern was puzzling. This is actually good news. If we already understood everything, there would be no point in continuing to explore and study. The existence of mysteries means there are still discoveries to be made, still questions to be answered, still knowledge to be gained. 3I Atlas showed us that even in our own small corner of the galaxy, in our own solar system, which we've been studying for centuries, we can still encounter things that surprise and puzzle us. The philosophical implications are worth considering too. For most of human history, everything we could study and interact with came from Earth or from our solar system. Meteorites occasionally brought extraterrestrial material, but these were still pieces of our own solar system, fragments of asteroids or possibly comets that had orbited the sun for billions of years. With the arrival of ʻOumuamua and now 3I Atlas, we're suddenly able to study material that formed around other stars. We can touch, at least through our telescopes, matter from distant stellar neighborhoods. This is a profound expansion of our reach and our knowledge. We're no longer confined to studying just the products of our own star and planetary system. We can sample the diversity of the galaxy itself. This raises interesting questions about how representative our own solar system is. Is Earth typical or unusual? Are the planets orbiting our sun similar to planets elsewhere, or are we an oddball system? Do most star systems produce rocky inner planets and giant outer planets like ours, or are other architectures more common? By studying interstellar objects, we can begin to answer these questions. Each visitor carries information about conditions elsewhere in the galaxy. Collect enough samples from enough different sources and patterns will emerge. We'll learn which features of our solar system are universal and which are peculiar to us. The study of interstellar objects is also prompting new thinking about planetary defense. Earth is occasionally struck by asteroids and comets, impacts that can cause damage ranging from local destruction to global catastrophe. Most of these impactors come from within our solar system, and we're getting better at detecting and tracking them. But what about interstellar objects? They approach from unexpected directions at high speeds. Could an interstellar impact threaten Earth? The probability seems very low based on how rarely we detect interstellar visitors, but it's not zero. Scientists are beginning to consider how we might detect and respond to an interstellar threat if one appeared. The high velocities involved make deflection much more challenging than for solar system objects. Fortunately, most interstellar objects seem to be relatively small. Both ʻOumuamua and 3I Atlas were probably less than a kilometer across. An impact from an object this size would cause regional destruction, but not a global catastrophe. Still, it would be bad. The impact energy would dwarf any nuclear weapon. The explosion would be visible from space. The local area would be devastated. So even though the risk is small, it's worth thinking about. Detection systems designed to find asteroids could also spot interstellar intruders if they come close enough. Early warning of even a few months could allow evacuations or other preparations. Deflection might not be possible given the high speeds, but at least we wouldn't be caught completely by surprise. The media coverage of 3I Atlas was extensive but sometimes sensationalized. Headlines suggested alien origins or mysterious properties that the actual data didn't support. This is frustrating for scientists who have to constantly clarify and correct misunderstandings. But it's also a sign of genuine public interest in space science. People are fascinated by the idea of interstellar visitors. They want to know what's out there. The challenge is to channel that interest into accurate understanding rather than sensational speculation. Scientists working on 3I Atlas tried to communicate clearly and accurately through press releases, interviews, and social media. Some created videos and blog posts explaining their findings in accessible language. Education is another important aspect of discoveries like this. 3I Atlas provides a great case study for teaching students about orbital mechanics, spectroscopy, observational astronomy, and scientific reasoning. Teachers can use the real data to show students how science works. They can discuss how scientists form hypotheses, test them against observations, and revise their ideas when the data doesn't fit. This is much more engaging than abstract textbook examples. Students can see that science is an active, ongoing process, not just a collection of facts to memorize. Some educational programs have already incorporated 3I Atlas into their curriculum, using it to teach concepts ranging from Newton's laws to chemical spectroscopy. The discovery of interstellar objects is also changing how we think about contamination and planetary protection. When spacecraft visit comets or asteroids in our solar system, there's concern about potentially contaminating them with Earth microbes. Conversely, when we bring samples back to Earth, we need to ensure we're not bringing back anything hazardous. These concerns become more complicated with interstellar objects. If we send a mission to 3I Atlas or a future visitor, should we worry about contaminating material from another star system? If we brought samples back, would they need extra quarantine precautions? These are questions that planetary protection officers are beginning to wrestle with. The answer probably depends on whether the object has any chance of harboring life. Based on what we know, small icy objects like 3I Atlas are unlikely habitats for life. They're too cold, too small, and too irradiated. But we can't be completely certain. Life is remarkably adaptable and might exist in forms we haven't imagined. A precautionary approach would treat any extraterrestrial material as potentially biohazardous until proven otherwise. This might seem overly cautious, but the potential consequences of being wrong are severe enough to justify caution. One contamination event could be catastrophic if we brought back microbes that turned out to be harmful. The long-term plan for studying interstellar objects involves building better detection networks. Current surveys find maybe one interstellar visitor every few years, but these surveys aren't optimized for finding such objects. They're designed primarily to find asteroids and comets from our own solar system. A survey specifically designed to find interstellar objects would look different. It would focus on detecting objects with unusual velocities and trajectories. It would cover the whole sky frequently to catch objects as early as possible when they're still far away. Some scientists are advocating for a dedicated interstellar object detection system that could find dozens or even hundreds of such objects per year. With more detections, we could start to do statistical studies. Are interstellar objects mostly icy like comets, or rocky like asteroids, or a mix? What sizes are most common? Do they come from particular directions in the galaxy or randomly from all directions? Are there different populations with different properties? These questions can't be answered with just 2 or 3 examples. We need tens or hundreds of detections to establish patterns. But once we have those patterns, we'll understand much more about the population of objects wandering between the stars. Some researchers have proposed using artificial intelligence and machine learning to search through telescope data for interstellar objects. The amount of data generated by modern surveys is enormous, far too much for humans to examine carefully. Automated systems scan the data looking for anything unusual, but they're tuned to find solar system objects and might miss interstellar visitors that behave differently. Machine learning algorithms could be trained to recognize the signatures of interstellar objects by learning from ʻOumuamua and 3I Atlas. These trained algorithms could then scan future data more effectively, potentially finding objects that current systems would miss. The possibility of sending a probe to intercept an interstellar object is becoming more realistic as we learn more about them. Such a mission would be challenging but potentially achievable with current technology. The main obstacle is the speed. Interstellar objects are moving fast, typically 20 to 30 kilometers per second relative to the Sun. Matching that velocity requires a powerful rocket or a clever trajectory that uses planetary flybys to gain speed. Several mission concepts have been proposed. Some would send a small probe on a fast trajectory to intercept a newly discovered object. Others would position a fleet of probes in the outer solar system, ready to activate when an interstellar visitor passes nearby. The scientific return from such a mission would be extraordinary. Close-up observations and measurements would reveal details impossible to see from Earth. A probe could analyze the composition with high precision, measure the strength and texture of the surface, study how the object responds to sunlight, and perhaps even collect samples of gas and dust. If the mission included a lander, it could measure properties of the surface directly, drill into the interior, and send back detailed imagery. All of this would transform our understanding of interstellar objects from sketchy inferences to detailed knowledge. The engineering challenges are significant but not insurmountable. The probe would need to be small and light to achieve high velocity with available rockets. It would need autonomous navigation since communication delays at large distances make real-time control impossible. It would need to operate in extremely cold conditions since interstellar objects are typically far from the sun. And it would need to work reliably despite not having a chance for testing in the actual mission environment until launch. These challenges are similar to those overcome for missions to comets and asteroids in our solar system, just pushed to greater extremes. Funding such a mission is perhaps the biggest challenge. Space missions are expensive, and a mission to an interstellar object would cost hundreds of millions or potentially billions of dollars. Convincing funding agencies and government officials to allocate such resources requires making a strong case for the scientific value. The observations of 3I Atlas by Webb help make that case by demonstrating that interstellar objects are scientifically fascinating and worth intensive study. Every discovery raises the profile of the field and increases the likelihood that future missions will be approved. In the meantime, astronomers will continue using telescopes like Webb to study interstellar visitors as they appear. Each observation adds to our knowledge. Each object teaches us something new. The pace of discovery is accelerating as our instruments get better and our techniques improve. 20 years ago, we didn't know interstellar objects existed. 10 years ago, we suspected they existed but had never seen one. Now we've observed at least 2 in detail, and we're developing the capability to study many more. 20 years from now, the study of interstellar objects will probably be a routine part of astronomy with well-established methods and a large catalog of examples. The impact of these discoveries extends beyond astronomy. They influence how we think about our place in the universe. Knowing that objects from other star systems pass through our neighborhood regularly makes the galaxy feel more interconnected. We're not isolated in our little bubble around the sun. We're part of a larger galactic ecosystem where material flows between stars, carrying information about distant places. This perspective is humbling and inspiring at the same time. It reminds us that Earth is one small part of a much larger cosmos, while also showing that we have the ability to reach out and study that cosmos. The questions raised by 3I Atlas will occupy scientists for years to come. Some questions might be answered relatively quickly as more data is analyzed and published. Others might remain open for decades until more observations of similar objects provide context. And some questions might lead to completely new lines of research that we can't yet anticipate. This is the nature of exploration and discovery. You start with one question and end up with 10 new ones. Each answer opens new doors and reveals new mysteries. The process is endless and endlessly fascinating. Looking at the bigger picture, 3I Atlas represents one step in humanity's ongoing journey of cosmic exploration. We started by studying what we could see with our eyes. Then, we built telescopes and saw farther. We sent probes to other planets and landed on the moon. We built space telescopes that showed us the universe in wavelengths our eyes can't detect. And now we're beginning to study material from other star systems. Each step expands our knowledge and capabilities. Each discovery builds on previous ones. We're accumulating a vast body of knowledge about the universe that would have seemed impossible to our ancestors. The journey continues. New telescopes even more powerful than Webb are being planned. New probes to explore the outer solar system and beyond are being designed. New detection systems to find interstellar objects are being built. New scientists are being trained who will make the discoveries of tomorrow. The field is vibrant and growing, driven by curiosity about what's out there and determination to find out. 3I Atlas has contributed to this journey by showing us something we'd never seen before and challenging us to understand it. The object itself will fade away into the darkness of space, but the questions it raised and the data it provided will remain, continuing to drive research and inspire wonder for generations to come. The comparison between what we know about 3I Atlas and what we know about comets in our own solar system highlights both how much we've learned and how much remains uncertain. Comets in our solar system have been studied for centuries. We've sent spacecraft to several of them, landing probes on their surfaces and analyzing their composition in detail. We understand their basic structure. They're made mostly of water ice mixed with other frozen gases like carbon dioxide and methane. Rocky and dusty material is mixed throughout the ice. When a comet approaches the sun, the increasing heat causes ice to sublimate, releasing gas and dust that forms the characteristic coma and tail. This process is well understood and can be modeled mathematically with good accuracy. But 3I Atlas doesn't quite fit this picture. Its behavior is more extreme and more variable than typical comets. It's breaking apart more dramatically. Its composition includes organic molecules in unusual abundance. Its activity pattern doesn't match simple models. These differences suggest that either 3I Atlas is an unusual example even among interstellar objects, or that our models based on solar system comets don't apply well to objects from other star systems. Figuring out which explanation is correct will require observing more interstellar objects and seeing if they show similar properties, or if 3I Atlas really is an outlier. The fragmentation of 3I Atlas raises questions about what happens to interstellar objects after they break apart. The fragments we see trailing behind the main nucleus will continue moving through space on slightly different trajectories. Some might drift away and become separate objects. Others might crash into the main nucleus or into each other. Eventually, if the breakup continues, 3I Atlas might disintegrate completely into a swarm of small pieces rather than one coherent object. What happens to these pieces? Do they continue on the interstellar trajectory, spreading out along the path? Or do some get captured by the sun's gravity and end up in orbits within our solar system? The mathematics of orbital dynamics suggests that most fragments will continue on the interstellar path. They're moving too fast to be captured by the sun, but some pieces, particularly those ejected sideways rather than forward or backward, might have their trajectories changed enough to become loosely bound to the sun. These fragments would then be in very elongated orbits, taking millions of years to complete one loop. They'd spend most of their time in the distant outer solar system, far beyond the planets, only occasionally passing through the inner system. Finding these captured fragments would be extremely difficult because they'd be small, dark, and mostly very far away. But they might exist, remnants of interstellar visitors that didn't quite escape. The dust released by 3I Atlas will spread through the inner solar system. Some of it will be pushed outward by sunlight pressure, eventually escaping into interstellar space. But some will drift inward, possibly ending up in the zodiacal dust cloud that surrounds the sun. This is the faint glow you can sometimes see in the sky after sunset or before sunrise, caused by sunlight reflecting off dust particles orbiting the sun. Most of this dust comes from asteroids and comets in our solar system, but perhaps a tiny fraction comes from interstellar visitors like 3I Atlas. If we could collect and analyze individual dust grains from the zodiacal cloud, we might be able to identify ones that have the distinctive isotope ratios or chemical composition marking them as interstellar. Such particles would be incredibly valuable, pieces of other star systems that made their way to our neighborhood. The organic molecules detected in 3I Atlas connect to broader questions about the origin of life. Scientists have debated for decades where Earth's organic molecules came from. Did they form here on Earth through chemical reactions in the atmosphere and oceans? Or were they delivered from space by meteorites and comets? The answer is probably both. Earth likely received contributions from multiple sources. But understanding the relative importance of each source is important for understanding how life began. If most organic molecules had to form on Earth, then life requires very specific planetary conditions. But if space delivers abundant organics to every planet, then the raw materials for life are common throughout the universe. The organics in 3I Atlas support the idea that space delivery is significant. If an interstellar object is rich in organic molecules, and if such objects are common, then every planetary system receives a steady rain of organic material from passing interstellar visitors. The molecules delivered might not have been the specific ones needed for life to begin, but they could have contributed to the inventory of organic chemistry available for life to use. This makes the emergence of life seem less improbable than if every planet had to synthesize all its organics from scratch. The study of 3I Atlas also connects to the search for life on other planets. Astrobiologists are intensely interested in understanding what kinds of environments can support life. They study extreme environments on Earth where life manages to survive despite harsh conditions. They analyze the atmospheres of planets orbiting other stars, looking for chemical signatures that might indicate biological activity. And they try to understand the chemical pathways that could lead from non-living molecules to living organisms. Every piece of information about organic chemistry in space is relevant to this quest. The molecules in 3I Atlas show that complex organic chemistry happens naturally in cold, icy environments. This might be relevant for understanding life's potential on icy moons, in our solar system like Europa or Enceladus, which have liquid water oceans beneath their frozen surfaces. The way 3I Atlas responds to sunlight provides insights into how materials behave in the space environment. Engineers designing spacecraft need to understand how different materials respond to solar radiation, extreme temperatures, and vacuum conditions. The natural experiment happening with 3I Atlas shows how a mixture of ice, rock, and organic material reacts to these conditions. The fracturing, sublimation, and chemical changes are all relevant to understanding material properties in space. This knowledge feeds into better spacecraft design, helping engineers choose materials and structures that will survive the harsh space environment. The societal impact of discoveries like 3I Atlas should not be underestimated. While the immediate practical applications might seem limited, the long-term effects are profound. Major scientific discoveries change how people think about the world and their place in it. The Copernican revolution showed that Earth is not the center of the universe. Darwin's theory of evolution showed that humans are part of nature, not separate from it. Einstein's relativity showed that space and time are flexible, not absolute. Each of these discoveries transformed not just science but philosophy, culture, and society. The discovery that interstellar objects visit our solar system is smaller in scale but still meaningful. It shows that our solar system is not isolated. We're connected to the broader galaxy through the flow of matter between stars. This connectivity has philosophical implications. If material from other star systems can reach us, then material from our solar system can reach other star systems. Pieces of Earth blasted into space by asteroid impacts might even now be traveling between the stars. Some could eventually land on planets orbiting other stars. If those planets have the right conditions, Earth material might seed them with organic molecules, or even with hardy microbes that survive the journey. This idea, called panspermia, is speculative but not impossible. It suggests that life might spread naturally through the galaxy without needing intelligent intervention. Each star system becomes a potential source of life for others. Whether this actually happens is unknown. The odds of a rock from Earth surviving the journey and landing on a suitable planet seem incredibly low. But the galaxy is old and large. Even incredibly unlikely events happen occasionally given enough time and opportunities. The existence of interstellar objects like 3I Atlas shows that material does travel between stars. Whether that material ever includes viable organisms is an open question that might take centuries to answer, but it's a question worth asking and studying. The technological requirements for studying objects like 3I Atlas drive innovation in multiple fields. Better telescopes require advances in optics, materials science, and control systems. Better detectors require progress in semiconductor physics and cryogenic engineering. Better data analysis requires improvements in computing and algorithms. Each of these technological pushes benefits society broadly. The sensors developed for astronomy find applications in medicine and industry. The computational techniques developed to process telescope data get used in artificial intelligence and data science. The materials developed for spacecraft get used in consumer products. The chain from basic research to practical application is sometimes long and indirect, but it's real and valuable. The careers of the scientists studying 3I Atlas span the full range from students just starting out to senior researchers near retirement. Each brings different perspectives and expertise. Senior scientists have deep knowledge and experience that helps interpret complex data. They've seen similar phenomena before and can draw on decades of study. But they can also be set in their thinking attached to established ideas. Younger scientists bring fresh perspectives and willingness to challenge assumptions. They're often more comfortable with new technologies and methods. The mix is important. Science advances best when different generations work together, combining wisdom and innovation. The collaboration extends beyond professional scientists to include amateur astronomers and citizen scientists. Amateur astronomers, with their own telescopes and passionate dedication, sometimes make important discoveries. They spot new comets, track asteroid positions, and monitor variable stars. Their contributions are valuable and increasingly recognized by the professional community. Citizen science projects allow members of the public to participate in research by classifying images, analyzing data, or running computations on their home computers. These projects engage thousands or millions of people in scientific work, distributing tasks that would be impossible for small research teams to handle alone. 3I Atlas observations benefited from this collaborative approach, with amateur astronomers providing some of the early tracking data that helped establish the object's trajectory. The economic value of astronomy is sometimes questioned, but it's more significant than many realize. The astronomy industry employs thousands of people in high-skilled jobs, from engineering to data analysis. Universities with strong astronomy programs attract students from around the world, bringing tuition dollars and enhancing reputation. Companies that supply instruments and components to astronomical observatories develop expertise that's valuable in other markets. The tourism value of astronomical facilities brings visitors and revenue to remote locations. And the inspiration provided by astronomical discoveries motivates young people to pursue careers in science and technology, building the workforce that drives economic growth in a knowledge-based economy. The philosophical questions raised by 3I Atlas touch on deep issues about existence and meaning. What does it mean that we can study material from other star systems? Does it change our understanding of humanity's place in the cosmos? For some people, astronomy provides a sense of perspective and humility. We're small compared to the universe, living on one planet among trillions. Our existence is brief compared to cosmic timescales, yet we're capable of understanding that universe through science and reason. We can look at an object that formed around another star billions of years ago and figure out what it's made of and where it came from. That capability is remarkable and worth celebrating. For others, astronomy raises questions about meaning and purpose. If the universe is so vast and we're so small, does anything we do matter? This is an old question without easy answers, but many find meaning precisely in the act of understanding. The universe doesn't care about us, but we care about the universe. Our ability to study and appreciate the cosmos gives our lives purpose and meaning. The fact that we're here to ask these questions is itself remarkable, perhaps even meaningful. These philosophical reflections often accompany major scientific discoveries, showing that science is not separate from human concerns, but deeply connected to how we understand ourselves and our place in existence. The future observations of interstellar objects will benefit from lessons learned with 3I Atlas. Scientists now know what kinds of data are most valuable and how to obtain them quickly. Before an object moves too far away, they've developed analysis techniques specifically for interstellar visitors. They've established collaboration networks that can coordinate observations across multiple telescopes. All of this preparation means that when the next interstellar object appears, the response will be faster and more effective. The scientific return will be greater. Each successive observation builds on previous ones, accumulating knowledge and refining techniques. This is the progressive nature of science, where each discovery enables the next. The public engagement with 3I Atlas demonstrates appetite for space science stories. Media coverage was extensive, though sometimes focused more on speculation than established facts. Social media saw intense discussion and debate. Public lectures and planetarium shows featuring 3I Atlas drew large audiences. This interest is valuable and should be nurtured. An informed public that cares about science is more likely to support funding. For research and education, Scientists have a responsibility to communicate clearly and honestly, helping people understand both what we know and what remains uncertain. This builds trust and maintains public engagement with science. As we look ahead, the study of interstellar objects will become increasingly sophisticated. Future telescopes will be able to detect smaller and more distant objects. Spectroscopic techniques will improve, allowing identification of even more complex molecules. Computer models will become more realistic and predictive. And eventually, we might send spacecraft to visit interstellar objects up close, providing ground truth data that validates or refutes our telescope observations. Each advancement brings us closer to comprehensive understanding of what travels between the stars and what it can teach us about the galaxy. The legacy of 3I Atlas extends beyond the specific scientific results. It represents a milestone in humanity's exploration of the cosmos. We've moved from observing the sky with naked eyes to studying material from other star systems with advanced space telescopes. That progression took thousands of years of cumulative effort by countless individuals. 3I Atlas is one data point in that long story, but an important one. It confirms that interstellar objects are real and accessible to study. It shows that they have properties worth investigating. And it motivates continued investment in the tools and techniques needed to learn more. In that sense, 3I Atlas has already achieved lasting significance regardless of what future research discovers. It's part of the historical record of human exploration and understanding, a stepping stone to whatever comes next in our quest to comprehend the universe we inhabit. The observations of 3I Atlas will continue to yield insights for years as scientists refine their analyses and develop new interpretive frameworks. Raw data that seemed confusing initially might make sense when viewed through new theoretical lenses. Unexpected connections might emerge as researchers from different fields compare notes and combine perspectives. This is how science works. Data collection is just the beginning. The real work of understanding takes time, collaboration, and creative thinking. Webb gave us the data. Now human ingenuity must extract meaning from it. What makes 3I Atlas truly special is that it forced us to confront our assumptions. We thought we understood comets. We thought interstellar objects would be similar to solar system objects. We thought we could predict behavior based on established models. But 3I Atlas showed us we were missing something. Maybe our models are incomplete. Maybe interstellar space produces objects different from anything in our solar system. Maybe the diversity of the cosmic objects is greater than we imagined. These revelations are valuable. They push us toward better understanding. The story of 3I Atlas is ultimately a human story. It's about curiosity driving us to explore. It's about ingenuity creating tools to study distant objects. It's about collaboration bringing together people from around the world. It's about persistence in the face of puzzles and mysteries. And it's about wonder at the magnificent complexity of the universe. These human qualities have driven every great discovery in history. They'll continue driving discoveries in the future as we reach ever farther into the cosmos, seeking to understand what's out there and what it means for us.